this particular terms to this particular connection, then you will get the expression for this particular case, right? So try to work it out for the heat flow rate. So that is what is the heat flow rate that you are going to arrive. So I have given the enough information. So whether you are applying in terms of gamma by gamma minus 1 into mr T1 minus T2, and this delta H is equal to mCp T2 minus T1, that Cp is nothing but equal to gamma R by gamma minus 1. And finally, what is the expression that you are going to get? So isentropic means entropy remains constant. Isentropic means entropy remains constant. So that things the student has to understand. So here, and the drawing the PV plane, that is also important. So you should not forget that drawing the PV plane. So the isentropic process. So this is the isentropic expansion, right? And this is represented as PV to the power of gamma is equal to constant, and this is all the work done. This is all the work done, right? So this W is nothing but equal to minus VdP, this work, right? After obtaining the expression, then you will get this particular final relation, either this one or either this one. So these two are there, right? But for a closed system, and if you observe that for a closed system, how you can get that PV plane, right? How you are going to get that PV plane? Try to observe here. Try to observe here. So that is take this particular plane PV, right? The system changes from state 1 to the state 2, and it is PV to the power of gamma is equal to constant. So this is the area. This is the area in isentropy or reversible adiabatic process. So this is nothing but this W is nothing but equal to integral of PdV. This W is nothing but equal to integral of PdV, right? This is how the relations are there for the closed system and also for the open system. Okay. So these are the, that is for the isentropic process. So try to work it out for the heat transfer in isentropic process with the available data, and find out what you are going to be getting from this particular studies. Find out what you are going to be getting from this particular studies. That means, yes. Now come to the polytropic process. So what is the polytropic process? So the polytropic process is represented as PV to the power of n is equal to constant. PV to the power of n is equal to constant. And the after solving the expression for the, that is drawing the PV plane, this is the polytropic expansion. This is the polytropic expansion, PV to the power of n is equal to constant. Then system changes from state 1 to the state 2. Then the work transfer, that is the W1 to 2, you will get it as n by n minus 1 P1 V1 minus P2 V2. Then this is MR, that is let me write as here n by n minus 1, n by n minus 1, m r t1 minus t2, n by n minus 1, right? Or else, let me write once again. So that is equal to n by n minus 1 t1 v1, that is nothing but equal to mr t1 minus t2. So this is the work done. Apply the first law of a thermodynamics, that is delta H plus W122, and this W122 is nothing but this is the expression you have to use. Then already it is discussed that the delta H, it is nothing but equal to mCp T2 minus T1, mCp T2 minus T1. Then what about this particular gamma? That Cp is nothing but equal to gamma R by gamma minus 1, and Cv is equal to R by gamma minus 1. So either of the thing you can select that one, and finally you can get the expression for the open system. So try to derive the expression for Q1 to 2 is equal to what is the expression that you are going to be getting by using that particular. So this is the thing which is left to you. So in case of a polytropic process, what you are going to be getting. So strictly when you observe the PV planes onto this side, so what is meant by, what is the basic difference between how it can be represented, the polytropic process, or how it is represented onto the temperature versus entropy plane. So the PV plane representation, especially for the thermodynamics point of view, it is more necessary. So when you draw the PV plane, that is the P, V, and this is the constant pressure process. This is the constant pressure process, and this is the constant volume process. Here n is equal to 0. Here n is equal to infinity. And the first step which you are going to be getting is isothermal process, that is the PV. The direction is also important. PV is equal to constant. This is the isothermal process. Next, after then, you will get the polytropic process, PV to the power of n is equal to constant, right? The next one is this one. So this is PV to the power of gamma is equal to constant. Now you observe all the area involvement in a PV plane for the different process. So what about the area for this one? That means here, what about the work you are going to be getting for a closed system? For a closed system, that you should not forget about this pattern. For an open system, that is how to draw the open system, that is already it is shown there, right? And this is for a closed system. For a closed system, so the area involvement only onto this one. For the open system, so this is what? This is the area, right? This is the isothermal process, that is PV is equal to constant, right? PV is equal to constant. That is when a system changes from state 1 to the state 2. Next one is this is the polytropic process, right? and the next one is this is the PV to the power of gamma is equal constant. PV to the power of gamma is equal constant, right? So this is the P versus V plane representation, P versus V plane representation, and the for the flow system, here you have to write it as W is equal to, for a polytropic process, it is N by N minus 1 P1 V1 minus P2 V2, that is nothing but equal N by N minus 1 MR T1 minus T2. But for this case, the closed system, it is P1 V1 minus P2 V2 divided by N minus 1, that is equal to MR T1 minus T2 divided by N minus 1 divided by N minus 1. So the area involvement, try to observe the, what about the work done for a closed system in isothermal, in isentropic process? What about the work done for a closed system in polytropic process? What about the work done in closed system for isothermal process? What about the work done in closed system for a constant pressure process? And here anyway, that is the work done in this case in a constant volume, it is 0. But the work done in constant pressure process is, work done in constant pressure process is 0 for a open system. 0 for a open system, right? So this is what where you should have to observe the drawing the PV planes representation for a closed system and also for the open system. Now there is a little bit difference that when you enter into the second law of thermodynamics, then you are going to practice, or you are going to draw the TS plane. You are going to draw the TS, or you are going to practice the TS planes, right? So let me show on to this one. So that is the temperature versus entropy. Temperature versus entropy. So in case of a isentropic process, in case of a isentropic process, that is entropy remains constant. So you will get the line as like this one. So this is nothing but 1 to 2. Whereas for the case of a polytropic process, then this is, right? This is the equation. That means entropy is slightly going to increase. Whereas this one is nothing but equal to PV to the power of gamma is equal to constant. PV to the power of gamma is equal to constant, right? So this is one. Next, there is another line, that is this is nothing but the constant temperature process. This is nothing but constant temperature process, right? Because in a constant temperature process, if you just observe that one here, when a system changes from state 1 to the state 2, T is equal to constant. That means T1 is equal to T2, right? Next, in case of a constant volume, so this is the constant volume process. This is the constant volume process 1 to 2. Next, there is the constant pressure process is there. So that is the constant pressure process. So system changes from state 1 to the state 2, right? This is how the represent. Why? Because here the isentropic process, the entropy remains constant. So this is what how to draw the lines. The entropy remains constant for this case. And polytropic, slight variation is there, slightly improvement in entropy, slight improvement in entropy. And temperature, that is the T1 is equal to T2, isothermal process, constant volume process, and constant pressure process, right? So this is how you have to practice for solving the numerical problems in case of a entropy also. So for today's class, what I have discussed today is that the developing the heat and work transfer relations for open system when it is subjected to the different process. For a constant pressure process, work done is 0. For a constant volume process, work done is V into P1 minus P2, right? Next, the isothermal process, W is equal to P1 V1 ln V2 by V1, or that is equal to MRT1 ln V2 by V1. In case of a adiabatic process, work done W is equal to gamma by gamma minus 1 into P1 V1 minus P2 V2. When the pressure and volume terms are not given, then you can write it as the work done is equal to gamma by gamma minus 1 MR T1 minus T2. In case of a polytropic process, work done is equal to N by N minus 1 P1 V1 minus P2 V2. When the pressure and volume terms data is not given and only the data is given on temperatures, then you can write the work done in a polytropic process for open system. W is equal to N by N minus 1 MR T1 minus T2. MR into bracket T1 minus T2. So these are the things that you can observe. Right? So this completes the today's lecture. This completes the today's lecture, that is the developing the heat transfer and work transfer relations for open system. Thank you one and all.